So now, according to the schedule, I'd like to speak about the DD multiscale modeling approach. So how dislocation dynamics is used in a multiscale modeling. Okay, so how could information from dislocation dynamics be transferred to a higher level model, typically finite element? Okay, that's the one that we are mostly interested in. Up to now, we saw that we were able to have some information transfer between MD to DD. Now I'm looking for DD to FEM and eventually to the whole set of scales altogether. So at the end of the day, you will have an example, a nice example from nano indentation typically, because I showed you that from nano indentation I was able to learn things regarding the dislocation loops nucleation system. I will do some nano indentation using DD. I will show you that this afternoon. And we did already, I showed you the nano indentation using FEM. So here we have the complete story on nano indentation for this using these three tools. So now let's focus much on the constitutive equations. So yesterday, when did we speak about that? Oh, it's so long I'm with you, I forgot, but it was yesterday? Or the day before yesterday. We derived this dislocation density model of crystal plasticity, where you had the flow law, which relates the shear strain rate. I just want to remember you. Shear strain rate to the shear stress on a given slip system S at a given power. And here is a critical isotropic hardening. Remember that this was isotropic and not kinematic. And this isotropic stress is changing with the dislocation densities on all the slip systems, possibly the 12 of them. And this now dislocation density can evolve with a production term. So you have more and more dislocation density with the strain here, minus an annihilation term that occurs when two dislocations annihilate when they are too close inside this radius here. So DD could be used, it's a nice tool to use if you want to compute those parameters. If you want to compute, here there are very few parameters by the way, it's a physically based model, so the number of parameters is quite low. Of course this is a matrix, so it looks like a big set of parameters, but we saw with the junctions when I spoke about the hardening, that this is just a 12 by 12 matrix that could be reduced to half because it's symmetric. And then if you remove all the symmetry between the one-on-one planes, you only have 6 parameters which are independent. So here you have only 6 values to compute, and those are more or less the same. K is a mean free path that you need to be computed, and beta R you need to compute. So how can we do that using DD? Using DD, things are quite simple. What you can do is that you can put a dislocation line like this on the system S. Let's say it's an orange dislocation is on S. You put many dislocations on the system U, as forest dislocation like that, of all orientations. Because I told you if you put all the same orientations, dislocations which are lazy, will find the angles for which the interaction is the minimum. And then it will go through for free. We did that to analyze some, let's say, GND hardening with a colleague of mine, Samuel Forrest, that you may know if you are dealing with crystal plasticity with length scale. We were looking at the effect of dislocation in a polarized dislocation density. This is not a good idea. If you make your polarized forest, so all the same sign, all the same orientation, incoming dislocation will rotate, find the way the interaction is the easiest, and go through. So you will always find the very bottom line of the hardening. In reality, since you have all the possible orientations, the hardening is a lot higher than that. So you cannot do this artificial setting. But the artificial setting you can do is to put your dislocation density of all possible orientations, but not a single one. All possible orientation, all signs, all orientation. And that way you will have a statistic of the dislocation passing through the obstacles. So out of that, you can compute for each slip system interaction the interaction coefficient A. You can make this calculation quite easily, like that. And you will find that globally, if you do it, I would say nicely, you will get something close to 0.009 for this value. If you take out, it will be 0.3. This is typically the usual relationship people are using for Koch's law, 0.3 mu b square root of total dislocation density. This is typical of FCC material. Okay. I told you that we can do much better. I will go back to that. And typically the paper from Devinck and co-workers in 2008 will more explain that. I will go back to this. Will more detail those values. For the main free path, the same thing was done. So I computed in the DD code, but so in that case was for large-scale simulation. I computed the number of obstacles the dislocation was encountering before being totally stuck in the sample. Or you can fit the curve, you can fit your dislocation density evolution curves with some law, and out of the fitting of the curve, you can derive the parameters which are involved in this production law. Okay, so the mean free path could be computed out of a large-scale simulation of dislocation dynamics, for example, in tension, or you see globally. You can also compute the annihilation distance, so the radius at which two dislocations will be totally annihilated, which is a Feuberger's vector, like that. So this is just easy parameters that we can compute using DD. Very hard to compute using, to measure experimentally, actually, because experimentally it's impossible to measure the strength of the systems with another systems. You always have all the systems together. You cannot isolate one or two and make an average. It's impossible. So this is where I would say DD is a very nice tool, okay? I think you can use it like that. It's a tool to measure something which is not reality. In reality, you will never have such an interaction between only two slip systems. But with DD, you can do that. So you have access to parameters of this model. So I think that's the nice thing of dislocation dynamics. Do you get the idea? You see? I think this is something you can use. So as I said in my introduction, you should have a look, a very serious look to that work from Devin, Croc, and the co-workers in 2008. And typically, I don't know if I put it, yes, this is the work. So those are two references I give you. And I wanted to sum up their work yesterday night with my crash computer. I was not able to do that. But you can have a look to those two papers. One is published in Science, one is Acta Materialia. So what did they do? The idea is the same. I cannot write down the equation because of this stupid computer, but what they change is this thing. Typically, you see, it concerns the dislocation mean free path and the string hardening. This is the same. Dislocation storage. So what did they do? Is they just change this expression here. So in this paper, typically, they improved a bit this formula. It's just an improvement. It's not a big change. It's an improvement where they take into account in that mean free path here all the different type of junctions. I mean that they assume that it's not the equivalent if a slip systems encounter another one, if a Lombard-Cottrell lock form, or if it's an earth lock which is forming, then K is not the same. You cannot just put a term here. You should also change K. And they also argue that you can add up some line tension effect. There is a logarithmic term now in their expression here, which enter into play in that expression. Okay. So in conclusion, if you're interested in crystal plasticity modeling, you can use such a set of equations. I think they are very good equations. You can even be closer to the theory, to the experiments, by changing a little bit this expression using what they propose. I'll let you read the paper if you want. I have it here, by the way, if people want it. And you can change this equation to have it closer to the experiments. But this is what I think a good way to tackle down continuum scale modeling using a dislocation density based equations. Okay, so have a look to that paper. And I showed you yesterday that this was able to reproduce a nano indentation test, or 2 days ago, nano indentation test using crystal plasticity finite element modeling. Okay. So this was what I want to show you here. So this is what I showed yesterday. Remember, so this now, if you put that in the finite element code, you will have a typical hardening matrix in the meaning of mechanicians. This is the hardening matrix H, where you have all these parameters. So here in the assembly, I know that some of you use the UMAT, subroutine. In that UMAT subroutine, I'm sure you are dealing with such a parameter. So you enter that explicitly in your model. Except that here in my model, I have these dislocation densities as parameters, what we call it an internal variable, which is stored at each gauge point. And what is nice with that is that when we do your simulations, then not only you can plot the Von stress, but you can have access to the dislocation densities at every place in the samples. You can have access to all this, not all, but at least dislocation densities on all the slip systems in this thing. Okay. So do you get the idea? So I would not say much more on that. So only that you can compute this, and this. So this 3 set of parameters using dislocation dynamics with dedicated experiments. They are not something realistic. It's not done to mimic experiments, but just to dedicated experiments to measure the parameters. And the setup of parameters I gave you last time. So I hope you have it in your slide I gave you, because here I didn't have time to copy and paste. Okay? Before going, maybe I can go further a little bit. I remember that for the kinematic hardening, I told you kinematic hardening is another story. Kinematic hardening depends so much on the boundary conditions that, like this typically, if you have this feature, when you unload, it will be easier than when you load, because when you load here, there is some obstacles which are interacting. Here you have some extra hardening due to the R1 looping. If you were unloading the dislocation when it is here, it will be attracted by the other dislocation, so this will be much easier. So it means that if you do a cycle, it will be hardening. When you unload, it will be very easy to unload. So this is typically the signature of kinematic hardening. If you go back to the slides I showed you 2 days ago, you have this feature. I should have put it here. But, okay? So this depends a lot on this. For example, for precipitate, for the shape is even worse, because here you, depending, this is the same volume fraction, so you have the same volume of the material, except the size is different, the shape ratio is different. And here, if you load and you unload, when you unload, you can see here the kinematic hardening is exactly the slope of this curve here, which is different in all the cases. You don't have, so here it's a full simulation with all the slip system active, and you can see that the slope depends much on the size, the shape ratio of the material. Okay? So if you want to derive some kinematic hardening equations for that, you need to think about it and to take into account the shape ratio, and which is not the same for each slip system. You see that the yellow one has a small path, the big one has a bigger path. So this has to be accounted for in your modeling. And this is important for what people call the Langford coefficient. I don't know if you are about to, if you know the Langford coefficient, which is the ratio of the two constraining strain when you are pulling in tension your specimen. So in FEM, we know that we cannot, with classical finite element modeling, we cannot reproduce this Langford coefficient effect, whereas with DD we can. So using those data, you can fit some model of kinematic hardening that will make this correct coefficient in crystal plasticity modeling. Okay, for that, I think what I want to spend now a few minutes on, with the help of Professor Sundararaman, is to answer a question I had also in previous lectures. I think I did it here on Linux, so it's very, very bad. But this was a PowerPoint file. I want you to say a few words on stereographic projection. I know that some of you were interested to understand what is stereographic projection. I think this is the place to speak about that. So because some of you said that we need to know what it is, and in dislocation crystal plasticity, we need these parameters. We need to know what system is active when you pull on a given direction and so on. So I think it's not clear for everybody of you what is the stereographic projection, how we were sure that if I was pulling along 1, 2, 3, only a system is active. If I pull on 1, 1, 1, another one is active or not. Is it clear for everybody, this? No? Okay, so I will spend a few time on that, just to make it clearer. So I wanted to have a very nice 3D view of the projection stereographic. This is where I crashed the computer, actually, when I started that yesterday. So I have a bad plot, but I have a very nice tool I will show you. Yeah. So this is how it looks like. So the methodology is like this. So this is something I compute in my 3ds code. When you have 3ds, we plot that. This is what we call a stereographic projection with this pole. Pole is 001. So what does it mean? So the techniques is like that. So you have, actually it's a way to project along a plane something which is on a sphere. So it was used for years, for ages actually. It was used, I think, in the ancient ages to represent the Earth. And this kind of spherical data you need on Earth was used with this stereographic projection. So the idea behind is that you take a given orientation or given point, for example, your point M here on the sphere, and you will represent the point projected on the plane here by M prime, which is there. So, so M prime is the intersection of the pole you are looking at. The pole is this guy, to the point you want to look, and this is M prime that you will print. Okay, you get this idea? So here I wanted to do that with 111, 120, and I'm not able to do that with LibreOffice. I cannot do that. With PowerPoint, I think I can do some nice animation on that. Okay. So what I want to do now, I think I will ask Professor Sundararaman to explain us why you have such lines which appears here. This 1, 1, 1. This corresponds to an orientation. So if I had done my cube, I would have put here the lattice, a cubic lattice, for example, here. And just assume that you have the 1, 1, 1 direction. 1, 1 direction is giving a line here that pierces the sphere at a given point. If I put back the point, it will fall here. So you have your 1, 1, 1 point here, the project there, and it gives this point here. Okay. And now the question I asked to Professor Sundararaman, who is an expert of this thing, because they use that every day in TM to know what is the Burgers vector of this dislocation, what is the slip direction, what is the slip plane normal, and so on. This is done. So he will explain you why you have such lines like this and lines like this, such contour you see between your planes. Okay. So I'll let him tell you. And I would say that the key points here is that this projection, and this is why it was used in literature, it conserved the angles. This is a big properties on that. It means that if you plot two lines here with a 90 degrees angle, in the projection you still have this 90 degrees angle. So this is why it is so much used in experiments or in analysis of 3D pictures. So maybe you can explain a bit, and then I will come back just after, because I have a very nice tool I will show you for the mechanical point of view, how we can use it now to compute speed factors and so on, okay? So I will show you. Maybe you should use one of the microphones.
Now what I will do is I will just draw this diagram. Okay. Essentially, the globe. Okay. So this somewhat represents a globe. You understand this? Okay. You can have a coordinate system. Okay. Comes out like this. That's what essentially which is being shown here, right? Suppose you have a crystal, you keep it here, look at the center. All the crystal planes, when we wanted to represent in a vector, representing a plane is very difficult, right? So you represent it with plane normals, right? And if you wanted to measure angle between two planes, if they are inclined like this, it's better to draw the plane normal and measure the angle. That is precisely what is being done in a stereogram. Okay. Suppose I draw plane normals, they will be meeting at some points on the surface, correct? That is essentially what is being done. Okay. With respect to this coordinate system, from here to here, with respect to z axis, this particular point, if it makes an angle, you assume that it's touching here. That angle which it makes it is theta. Okay. If I am viewing it from this side, I just put a torch or keep my eye from here on the surface of the sphere. Anywhere we can keep it. We assume that on this axis we keep, which is corresponding to 0, 0, 1. Then this is how the ray will come. From our eye, the ray has to come and meet here. Then from geometry, we find that this angle will be essentially theta, theta by 2, if it is theta, because this angle is theta, this angle which it will be submit will be 180 minus theta, then these are 2, okay. This you can, by whatever the trigonometry which you have studied in school, with which you can find out, okay. Then what is the distance if it touches this here on this surface, equatorial surface at some particular point, okay. What is this distance which is going to be? This distance will be essentially nothing but, if the radius is r, it will be r tan theta by 2. So every point on this equatorial plane here where it touches, okay, that r is the radius of that sphere. So essentially every point is related by tan theta by 2. That is how the representation is there. Okay. Is this clear? Right? Now, suppose we, to this line, we can draw, this is corresponding to a plane which is there in this one. This plane, when it meets the surface, it will be cutting the surface. Like this it will be cutting, right? Is this clear? This is how it is going to cut. Okay. Now, when this cuts like this circle is called as a great circle. Okay, but this will be a, if you look at the projection, this projection will be a curved line. For example, if we take this one with respect to a point here, okay, this is what essentially the axis is. And if this is the plane perpendicular, plane normal is this one which is cutting here, and this is the circle corresponding to it, correct? This will come at a point depending upon which direction which we view it. I said we can view it from anywhere, from here we can do it, okay. Then another important aspect of it is, which is important is, suppose this point is there, all the points on the surface of the sphere which are making equal angle with respect to this, okay. If you try to do that, that projection also is going to be, that will be a circle. That projection on this surface is also going to be a circle. That is another property of the stereographic projection, okay. Essentially what is going to happen is that this projection will be there, and all these ones will come as a arc of a great circle, okay. Finally, if you try to look at this, this will turn out to be on the sphere and not, this you are familiar with, this is called as wolf net, okay. So generally from here to here a great circle which is there, when we look at the earth we call it as a longitude, the other as a latitude. So latitudes are all represented in this way and longitudes are all represented in this way, okay. And every 1 degree or 2 degree if we take it, we will be getting a plot. This plot is called as the wolf net, okay, wolf net. Wolf net, okay. This is one which is used as a calibration chart to measure all the angles. So always when we do stereographic projection, we have one, the wolf net, which is a standard projection which is there, where every latitude and longitude is with 2 degrees intervals it is marked. Okay, what I will do is tomorrow evening I will show you little bit pictures of this. Now I am just explaining it to you. You understand that, okay. So this, if you look at it, all the points which are going to be there on this, we know the latitude and the longitude, correct, or essentially we know the angular relationship. So whatever is the angular relationship which is going to be there in 3 dimensions, like here we have one point which is there, some other point may be, arc it may be coming somewhere, all of them have a projection on this circle where specific points which corresponds to a latitude and a longitude, and that essentially corresponds to an angle from the center, from here to here. If you make this projection, this angle also we know with respect to axis, okay. So what we have got it is, every point is specific and it represents in 2 dimension a 3-dimensional representation, okay. That is precisely what this is being shown, okay. Then another important property is, if this is what essentially it is a point pole, okay. If we look here, this circle, why this is called as a great circle, corresponding to this line, I can have a circle that's plane which is perpendicular to this. I can just draw any circle which is touching the surface of that sphere, but the one which has got the greatest perimeter is one which is passing through the center. So that is called as the great circle, okay. So now if you come back here, now if you can see that any point which is going to be here, okay, the 90 degree away from it is going to be this line, okay. And if you look from vector addition also, if this is 0, 1, 0, this is 90 degree, this is 90 degree. If you put a stereographic projection, because since angular relationships are there, you will be able to understand it, which I will explain tomorrow with some slides, okay. This is how exactly this is being created. So from here to here, if I put a stereographic projection and back measure it, between 0, 0, 1 and 1, 1, 1 or this one, all the angles are going to be 54 degrees, okay. That's the position which it comes. So advantage is that angular relationship in 3 dimension is represented in 2 dimension in a stereographic projection. You understand that? Okay. That is the important thing about it. Another is that, especially if you wanted to find out, let us take this stereographic triangle. So this is 0. By symmetry, if you look at for FCC, okay, this is 1. Here this angle will be 45 degree because the distances, if you see from here to here, linear distance, 45 degrees will come here, 90 degree will come here. That is because tan theta by 2 we write. So the distance are not going to be linear, but the angle is essentially what we are representing it. So here the distances will be small, and as we go away the distance will become. Okay. Is this clear? Now, so by vector addition we can find out this will be 101 plane. Okay. This will going to be 011. Okay. This is 001. Okay. This is 111. Like that all the planes are there. So if we look in a cubic crystal, we will have essentially, there are 48 will be there, the full sphere. If you look at it, 24 is what we are representing it here on this one side of it. Now, suppose we wanted to find out in this particular, suppose we choose an orientation of the crystal which is going to be here. Okay. Then what is the slip system which will be activated? You know, from Schmidt law, 2 angles are going to be there. One, the angle which it makes with respect to orientation, the slip plane, and the angle which it makes with respect to a Burgess vector. The product of that is what we call is the Schmidt factor, correct? So that maximum when it will be is both are going to be 45 degree or close to 45 degree, correct? So if I take with respect to this particular one, okay, any point if I take it, there is one pole corresponding to 111 because this is 111 pole, this is another 111 pole corresponding to perpendicular to it, there is the third one which is going to be there. From here to here anywhere if we take it, this is what it is going to be. From here to here it is 54, okay. From here to here it will be 70, here it will be 35. So within this angle, any point if you consider beam orientation with respect to a plane, the angle can vary between either 54 degrees or 70 degrees or 35 degrees, 36 degrees. So within that it's going to come, correct? Then this is 101. With respect to 101 if you consider it, here this is 45 degree, this is 35 degree, okay, 36 degree, and from here to here it is 60 degree. So for this particular one, okay, essentially this what, so, and with respect to 1 bar 1 bar 1, this is a plane, plane normal it is, okay, this normally called in stereographic projection as a pole in the projection. With respect to that, what is it going to be 90 degree away from it is essentially a great circle which will pass through it, any line which passes through it like this, and this point and this point, it's going to be 90 degree away from it, okay. Because just like I mentioned, this is 001 or if you say 100, all the poles which are lying at these points on the stereographic projection, they are 90 degree away. Similarly, from this one we can find out all the poles which are going to be 90 degree away from it. So we know that a Burgess vector is going to lie in the slip plane. So with respect to a plane normal, it makes an angle of 90 degree, correct? So that is essentially what we have done. And in FCC system, it is either 1 bar 1 plane if you consider, it's going to be either 110 or 101, and this will be 01 bar 1, okay. This if when we index it, it will come, okay. By vector addition if we index it, this and this if we add together, this will be 101. Here and here it is 01 bar 1, that is 01, it will be 01 bar 1, it will be turning out to be. So with respect to 101 if we see these two, so this is the one plane which has got a angle which satisfies the maximum cos theta value, okay, plane normal, and this is the one which satisfies with respect to a bias vector direction the maximum. So the product, if we take it, okay, compared to for this same point, instead of having an orientation here, I can have an orientation of the sample in this direction. With respect to that, for this plane, and if I consider it, the angle will be either that with respect to plane, the angle which with respect to B may be very small, but the bias vector will be more. Finally, the product, when you take it, the Schmidt factor will turn out to be small. So this way, we can identify what is going to be the slip plane. That is, if I choose any beam direction here, I can tell that this is the slip plane and this is the bias vector. That means this defines the slip system. Only this slip system will be active in this area. Similarly, for every, this is called as a stereographic triangle, because from symmetry argument, by repeating this, we can generate that entire system. And in fact, symmetry is something which we use every day in life. Okay, even when we think how to do it, we find that copying is a form of symmetry, right? We just put it there, and on another side you have said that you have copied, correct? And our thinking process, when we ask computer to do a work, we always use symmetry so that your computational time could be minimized. So it's quite natural. So that way we can look at it. So these are coming from symmetry. So we can find out that for each stereographic triangle, only one particular slip system is going to be active. You understand that? That's how we can mark specifically. Here it will be 1 bar 1 1, okay, 1 0 1 direction, and here if I try to do it, it will be 1 bar 1 1, okay, and the slip system will be 1 bar 0 1, I think, which will be active. Like that we can find out all these. Okay, these things one can calculate it and just show it here. So this is how we can find out what are going to be all the slip systems which are going to be there. Then another important factor, I think, as Marc has explained, suppose this is the orientation, initial orientation if we start with, okay. Then we know that when we deform that sample, the orientation continuously changes. What is the direction it will be changing? From here, if it tries to change, it will be changed towards what is going to be the bias vector direction. So it will go from here, and when it reaches here in this direction, then two slip system becomes active. Then it will start moving here and come to a point 1 1 2. So with respect to this, if you see this one as well as this bias vectors, both are making an equal angle. So two slip systems have got same Schmidt factor. So both the slip systems will be active. So under that orientation, when the sample rotation reaches that value, then we have two slip systems which are going to be active. Suppose we take, now let us look at 0 0 1, okay. With respect to this orientation, there are 4 1 1 1 planes are there. All of them are making an angle of 45 degrees with respect to it, making an angle of 54 degrees with respect to it. And in each one of them, if we take this particular 1 1 1, we have 1 bar 1 0, here it will be 1 bar 0 1 and 0 1 bar 1, 3 are going to be there. But this and the other one, okay, if you look at it, with respect to this one, it makes an angle which is 90 degree, which is far away, that line. But these two, if we look at it, makes an angle of essentially 45 degrees with respect to a beam orientation, and the slip plane makes an angle of 54 degrees. So both of them have got the possibility of both of them to operate. So with respect to 0 0 1 orientation, for every slip plane, there are two slip systems which can operate. That is why for this orientation, we will have 8 slip systems which will be active, which are equally probable. If we come here with respect to 1 bar 1 1, we can similarly calculate there will be 6 slip systems which will be active, okay. And if we come to this orientation which corresponds to 0 1 1 all these orientations anywhere which chooses which is 0, 1, 1 orientation of that sample, then we will have 4 slip systems which will be active. This you can do it as an exercise and try to find out the specific direction if we choose it, how many slip systems will be simultaneously activated for that beam orientation. Okay. And that this same thing we use it for not only for what are the applications of it. When we wanted to represent the point group and space group symmetry, they can be represented in the stereographic projection. Okay. Suppose I wanted to index a crystal diffraction pattern, like if the orientation of the beam is along 0, 0, 1, okay, all the poles which are lying on this great circle, which is called as a primitive circle, okay, they are all 90 degree away from it. And we know that once a zone axis is defined, all the diffraction spots, if you take the dot product with respect to a beam direction, it's going to be 90 degree. So using this, we can immediately index the diffraction pattern. Not only indexing the diffraction pattern, suppose I tilt the sample from here, okay, and bring it to another point, 0, 1, 1 orientation. Then if it reaches that point, what all spots which will come also will become very clear, because you can see immediately that this orientation of this part is 90 degree. So if when I tilt that sample also, the 200 diffraction spots which appear, they will not be rotating on the crystal, they will remain at the same place. This I will show you, I think this I explained on the first class, but I will repeat it again tomorrow and make it clear to you. Okay. So it has a lot of application in crystal plasticity also it has, but this is done for a stereogram is for cubic crystal. Suppose you are working on a crystal which is non-cubic, okay, we can find out the angular relationship between different planes could be calculated, okay, if you know the Sebae ratio. Then we can do that and draw similar type of stereograms can be drawn. These are called as stereograms for 0, 0, 1 projection. From this we can draw stereogram for 0, 0, 1, for 1, 1, 1. All these things could be done. Now there are softwares are available, interactive one, where you can just rotate it, you put the cursor on this and just rotate it, will just move and show the new stereographic projection. Okay. Then also I mentioned that we wanted the microscopy when we do, we want to know the foil normal. Okay. Foil normal is when the sample is introduced, okay, we are looking at some area at 0 tilt, okay, what is the normal to the surface. Once the normal to a surface is defined, we know what are the directions which are perpendicular to it, okay, what are angles other directions which make. From that we can decide, because generally in a microscope we can tilt the sample by maybe plus minus 45 or plus minus 30 degree. So if we tilt it by that much of angle, what are the diffraction vectors which are accessible for us with which we can image, do that. All this information will come out of it. Okay. Tomorrow I will explain it little, but I had given a basic idea. It's clear? Okay.
I can show you some application, MATLAB code that Christophe Després did. Up. Which is you see, you recognize the famous tool that Professor Sundararaman just explained. Here we just put all the orientation, 1, 1, 0, so this is the pole. The pole is 1, okay. You have this 90 degrees relationship. And on the right, you can see the Schmidt factors. Schmidt factors on all the slip systems. You have the 12 slip systems for FCC, which are plotted here. You can see the value here, okay. So this is assuming the Schmidt factors, you see that it's F cos theta sine phi, so it means that this is maximum at 0.5. When you will be at 45 degrees between the plane and the Burgers vector is also at 45 degrees, if you are pulling on that direction, here you will have the maximum shear due to a tension. This is called the Schmidt factor, the ratio between tau and sigma, and tau maximum will be half of sigma, okay? And this half is here, so this is the resolved shear stress. It could be maximum half and minimum 0, okay? And then I will move my mouse in the map, looking at the mouse, and it will automatically compute the Schmidt factors, assuming that this point indicates the projection of the tensile direction you put in your box. So let's just have a look. For example, if I put it here, okay? So you see that this will activate Which system? D1. It's clearly D1 which is active at that place, okay? And if I go back, you see I move a bit. I go back here, you can see that I will simultaneously activate 6 slip systems. Exactly, you see, the 6 components are active simultaneously. And what is nice with that symmetry, it's what we call a high order symmetry, is that the remaining 6 have 0. Okay, they are exactly 0. Okay, they are not a little bit loaded, they are not loaded at all. Okay. Now if you go in the standard triangle here, you see that here you are pure shear on B4. Okay, the B4, so this is typically B4 orientations. And if I go toward the boundary, so it will move toward the Burger's vector, which is bar 1, bar 101. It will move that way, and here simultaneously, a second one active, which is C1. Okay, B4, C1 are active. Okay. Now if I go back here, I will see that you have the 8 systems which are active again, and 0 between. Okay, 8 systems are activated. And this code is very nice. This is something he did, I think is very interesting. It's not only done this. This is assuming that you are pulling a tension along this axis, but you can put another tensor, and it will compute the stress, the shear stress, according to what you applied along that direction. Okay. And also you can pick up. If you click here, you can pick up the orientation. So you say that this is bar 203, and here it will give you the tensor and resolve shear stress on the 12 slip systems. Everything is given for you for free. You see. So this is something I think we use much in order to get this high symmetry of BCC, FCC crystal. So we can figure out that way all the possible orientations depending on where you are in your material. When you are loading your samples, what will be activated. So you can see 2 things. When we are in the double glide configuration, typically when we are here, at that place, although you have 2 which are mostly loaded, the others are also a little bit loaded. So it's not a highly symmetrical axis. This is the information I want to give you. When you are here, you have 8 active and 4 not active at all. Here you have 6 and 0 and 6 which are not. Here you have 2 which are most, and the others are also a little bit active. They are not this is not 0 here. You have a few Schmidt value at that place. Okay. So that way you better visualize, I think, what happens in a mechanical point of view, or again on the same map. So you click on it, and then you have your data. So this is what you take. You say, okay, I want to do in DD simulations. I want to pull on that direction. Here, you click on it. You look here. You pick up your stress tensor, which is given here in the crystallographic axis. You put that in Paradis because you're using Paradis, and you will have your loading corresponding to that if you want. Without any rotation, it's already done for you. Okay? That's a tool that you can use. MATLAB subroutine. Okay, I just wanted to show you what we do. Actually, in computing, we are always lazy, so we want to make some subroutine that can help you to set up your program. Okay, you all know that. And even worse, I think the young people are even worse than we were. They want something automatic. You cannot ask nowadays. You can ask a student to run 10 simulations. He wants to have something automatic that will run the 10 simulations for him. When we were doing our PhD, we were doing 1 simulation, and next day preparing the second one, and then the third one. We were doing all the simulation. Here, you prefer to work 1 week doing a single code that will prepare the 10 at 1 shot and run 1 shot. I think it's the same time at the end, but I know that you prefer automatic stuff.
No, and then the worst is that you realize that one assumption was not okay.
Yes.
And you continue.
You run everything for nothing. Yes, that's true. Yeah. Okay for this thing. So this, I think, illustrates well the continuum level. You see, this is all the possibilities that you can activate the 12 subsystem FCC material depending on your tensile direction. Okay. So I'm not sure I have much more to say because unfortunately I was not able to prepare the slides regarding the Vaincre work. But I advise you to have a look to this paper in order to check what they said. So if you have any question, I think we can stop here because now my next lecture is totally different. It's on boundary condition on dislocation dynamics. If I start now, it's totally different. So I want to keep it for this afternoon. Oh, this is. Oh, I don't remember what. You can have a look at the sources that are there. I can show you. This is only there. If you look at stereo, This is what he's using. I think there is something which is, you mean for this one? I think it's the package which is inside. MATLAB has no extra stuff.
MATLAB has
Yeah,
set up a GUI.
yes. Oh, GUI is automatic inside. But this is more than a GUI. So you have the pointer location, which is also taken out from your mouse. But it's inside, yeah.
An average, if you plot a MATLAB plot, there is this option to take your cursor anywhere.
Yeah, exactly.
And it will show you the values at least on the plot. Now
Yeah.
it is showing you the results of the calculation.
You see, this is done by this thing, which is get, the subroutine get, give it for you. So the summary of this study was, if you want to use crystal plasticity with a dislocation density based model, you can fit the parameters using dislocation dynamics with dedicated experiments that you do specify. This will give you all the isotropic coefficient very nicely. For the kinematic hardening coefficient, then this has to be done for each purpose, because there is no, today at least, there is no kinematic hardening rules available yet. There is one for fatigue. I gave you the references. And you can may find some for the crystal shape also. And I'm not aware of some of precipitate also there are. And that's it. Okay, so you wanted to say more words? Yes?
In fact, there are lots of slides are there, but what I will do is some essential features of stereographic projection I will try to explain. See, this you can see that this is any line which we draw from the center is radial. It's like an outward normal which comes and meets at this particular point, and you see that it makes a projection when we view it from here. As I mentioned, from geometry we can find out this angle, and this distance will be r tan theta by 2, correct? And the projection which we have taken is at the center, but this viewing direction, if you have it anywhere parallel to it, we can have the projection. Only thing is that it will get magnified. Okay. See, this is a plane and this is the plane normal. As I mentioned, why this is called as great circle is normal to this line. We can have a circle here also, right? Cutting it, planes which can cut it. But that will all make, if you look at the perimeter, which is going to be small, one which passes through the center will have the greatest perimeter or the area. So that is why that's called as a great circle in stereographic projection parlance. Okay. Now you see here, that's one point which is there. Like that we can have any point on the circumference of this circle. This is something like a latitude. If you take the projection of all of them, they will be cutting at different points. This will generate one which is a circle, correct? So like that, depending upon, this is the equatorial plane, and we can have so many latitudes which can be there, which each will be making a circle like this. So we will be making a concentric circles here. That's because we are viewing it from this particular point. In this particular one, if you look at this plane, so all the points which are going to be coming here like this, okay, they will be essentially making a line like this, correct? On this, when we view it from here, or all the points which are going to lie, the poles which are going to lie on this circle, in this plane, in the plane of the screen itself, they are all going to make a line like this in this projection, correct? This is essentially what happens. In this particular view, if we try to look at it, if we regularly take all the latitudes, okay, it will be like this. All the longitudes, this we have taken it like this, one, and then another one which we have taken it like two perpendicular to one. Anything which is inclined also, every one of them will make a line like this, okay. This projection is called as polar projection. This is one projection in which you might have seen that the representation of the earth is made like this also. So this we have studied in school, maybe in 5th or 6th standard, but we never knew that why this is being shown like that. Now we know that this is a stereographic projection where it's a sphere which we are trying to represent it in 2 dimensions. So all the angular relationship has to be maintained, okay. That's essentially what it's being done. And another important factor is that with respect to any point on the sphere, okay, if you take any pole, all poles which are making some angle, they will generate a circle. A circle on the sphere, only in stereographic projection that gets projected into a circle in the stereographic projection on the surface of the sphere. If you take any other projection, a circle will become an ellipse. That's one important property of a stereographic projection. Okay, that's what essentially is being shown here. Then initially we viewed from this direction. Okay, this is the plane. We can view it from here also. Keeping anywhere we can view it. So we get a projection. So they all are generating stereographic projection. From this direction, if you view it, with respect to an Earth, okay, if you look at it, this will be the east-west that projection which we see it, and the projection of this is essentially going. So all the points which are there on this one making an equal angle will be projected with respect to an equal angle on this. So, and this circle is called as the primitive circle in stereographic projection. Here, if you look at it, with respect to this one and another point, if we can take it this one, some angle they make it, but the projection when it comes, it is essentially r tan theta by 2. So how it will appear? Now if you look at it here in this projection, this is all, it's not going to be the same angle, angle will be depending upon as the angle increases, the distance also will increase. The same thing you can see it happening in the vertical one, if I with respect to a circle, the part of it. Then you should ask me what happens for the points which are going to lie here outside of it. Okay, all of them will be cutting this. If we keep a big screen here, outside of this circle, they will be coming and cutting. Okay, that's not being shown. In that case, what is essentially being done is that you project it from here, and whatever it appears here, it's being shown as a closed circle that will be represented as an open circle. So both the hemispheres are being shown in the stereographic projection this way. Okay. And now in this one, if you see, I am just showing the globe with all the latitudes and the longitude. We are viewing it from here, and this part of it, its projection essentially, what is important is that which will be coming within this equatorial, this great circle, okay, on the primitive circle, but the other part which is going to be there coming on the other side of it, for this one if you see it, that part will be projected outside of this primitive circle. Né? But one thing which I mentioned is that everything, a circle on a stereographic projection, circle on a sphere is always projected as a circle. So some part of the circle is inside, the other part of the circle is outside. From geometry we can calculate also what this angle is. If you know the angle, this is what I had shown it with projection, but we can calculate it also, okay, and then draw. But what is important is that when you see these sort of arcs, they are all arc of a circle in a stereographic projection, but the radius of the circle will be different. Okay. This way, if you take a latitude, again what is going to happen, this part of the latitude will be all the points on the latitude from here to here, they are all going to cut this primitive circle, some point here, but whereas those who are going to be outside, they will be coming. That's what is essentially represented. But this is another way in which we can theoretically calculate. Okay, we don't have to think of that projection. That part I am not going into, but you can theoretically simulate the stereographic projection. If you do like that, finally what you will be ending up with is, when we have taken a latitude and longitude here with respect to 2 degrees. This is called as the wolf net. Okay, if you see here, close here from the center, from this point when we are viewing it, all the latitudes and longitudes which are close by, they make a smaller, the linear distance is small, here the linear distance is going to be large, but the angular distance remains that same. Okay, this is the one which we, so this is one projection which we normally see of the Earth. Okay, this is how the, this is called as the wolf net, this is what we use it. This comes in standard sizes, or we can print it out whatever is the size which we want. Okay, and then superimposing on this, on a tracing sheet, we can draw a circle corresponding to that, on which all the exercise could be worked out. Okay, Here there are a lot of exercises are there how to measure the angle, but essentially what is important is that when we move from one point to another point, that is from one point here and another point, if I wanted to measure that angle, okay, we have to keep these 2 points either on a latitude or on a longitude, and then only we can, that gives the true angle. That is one of the restrictions which are imposed on that. Between any 2 poles we wanted to measure the angle, that is the way it has to be done. Now this is clear, this is how a stereogram is constructed. Some of the properties, that is a circle on a sphere will always be projected as a circle, whether it is a small circle, that is why the equatorial one which comes as a big circle, and all these things are arc of a circle which is being seen within the stereogram. Okay. You see this is on a sphere, at the center of it we have get a cube. Okay. All the plane normals could be drawn, they will be meeting at different points. The coordinate system is defined. Okay. Here it is 1 0 0, this is the way it is being defined. If 2 planes, if we consider it, the 2 plane normals are going to come here. Okay. But if you wanted to measure, and these planes, if you extend it, it will be cutting it like this, correct, on the surface of the sphere. Okay. And these plane normals, when we wanted to measure the angle between them, okay, this is essentially measuring a distance from here to here on the surface where the poles are getting projected. Okay. And you can make out that these 2 points are finally, when we are measuring this angle, they are lying on the surface of again a longitude, correct. That means that the points have to be brought either on a latitude or a longitude when we wanted to measure angle between 2 points. That is what is done in stereogram. Now I had just marked all the directions with keeping a pole. Okay, this is what is being done here, and you can see that from here to here, if I am viewing it from here, it will be cutting somewhere on this point. Now exactly different poles corresponding to different directions. Once the crystal coordinate system is fixed and we have kept it, we know all the poles where they are going to cut on the surface of the sphere. So those points are marked, and if you are viewing it from here, we can immediately make out that this is where they are going to cut the equatorial plane. Okay. This, if I just try to project it and see it, okay, this is what is going to be the 001 projection. Okay. That is exactly what we have got it. And in this, if I keep a wolf net behind it, we can immediately measure the angle from one point to another point. This is exactly what is being done using stereogram. This is exactly what is being shown here also. These for different angles if I wanted to measure it. But from here to here, if you have to measure it, because this is at one particular point, latitude and longitude, this is at another one, I have to rotate this and bring it so that this point comes on this one, because with putting a pin here, if I try to rotate it in this direction, then this point will come on that, so because this will remain at the center. Now I can measure, or I can rotate it in this way so that this point comes here, that way angle could be measured. That's what I said, to measure angle we have to do that. Otherwise that point we will say that this comes at some particular latitude and a longitude, that is the way we will be representing it. That is how it is done in geography. The other way we can do it is that the same thing we can calculate between different planes using this relation cos theta equals, okay, r1 dot r2 divided by modulus of r1 dot r2. With that also we can find out. That is what essentially is being given. This can also be used to generate a stereogram. Okay. This is stereogram corresponding to when the direction is 001. Suppose I want the direction to be 011 to be at the center. Then if I move it from here to here, okay, then this point will move from here to here, this point will move from here to here, all of them will move, because these moved from 45 degrees to reach here, the angle between them, then all this has to be moved 45 degree, but that movement will be on a latitude or on a longitude they will move. Here since this is moving on this latitude, all of them will move on a line, and this is what that projection essentially is. This is the same, all these aspects on a stereogram, whereas softwares are available. You can just put the mouse on it and just click it and bring it to a center. It will just rotate the stereogram and show you. This is exactly what is being shown here, where 001 was initially here and 112 was here. It's being rotated in this direction to bring 112 to the center. Then on all the latitudes, all these points are moved by that same angle of around 35 or 36 degrees. This is how we can generate any stereogram. Okay. That suppose it's a crystal is a tetragonal one. Then if the C/A ratio changes, we will immediately find that that angle between the different planes, between 001 and 110 90, but between 001 and 011 it's 45, but it's tetragonal. For this particular C/A ratio, this angle will change. When this changes, we can do such calculations using C/A ratio from crystallographically, and now we can see that the red circles, that corresponds to cubic system, and the blue ones are the ones which represent that same. This is like here it is 111, this is corresponding to a cubic system, 111 corresponding to tetragonal system which we have considered, this point comes here. Similarly here 011 comes here, but this is at 39 degrees, the angle between 001 and 011 in tetragonal system. This way we can generate a stereogram for the any system. Okay. And once such a stereogram is available, then it's very easy to find out if the crystal which you are trying to deform is going to be a non-cubic system. Now from this we can try to calculate which are the slip systems which are going to be active in that. Okay. That's what I had mentioned, that manually we can do it, or we can developing a software. And in fact in crystallography also, these sort of stereograms are used to represent different types of symmetries. So if you look at it, what are the types of symmetries which are there for point group symmetry and space group symmetry? I don't know, you people have studied all these? Symmetry in crystals, cubic symmetry in crystals is already represented in stereogram. For other crystals, what are the orientations which we can find out? That I will just leave it. Okay. Like when you deform a sample, which already Marc has explained how it will be taking place. That is, from here if you see that one slip system is active, okay, it will be moving towards from here to this direction, okay, this is the direction the rotation will be taking place of the slip plane, okay. Then from here it will come to 112, when it comes to 112, then if you look at it, both 1 bar 01 and 011 are making equal angle with respect to this. So two slip systems become active in this case. That how to dynamically view, already it has been covered. This is a stereogram where the same 001 stereogram is being shown which is a particular type of slip system which will be active if the beam orientation is within this. That is, it's possible that the beam orientation is 1 to 3 in this one, the sample which we are testing in. Okay. Suppose the beam orientation in another sample is 1 bar 2 3. Okay. Then this stereogram has to be considered. Then we know this is the particular slip system which will be active. All that information we can get from this. Okay. The rest of it you had seen it from the MATLAB projection. Okay. And here I had just given the values. Okay. And this can be used to find out when we have a crystals are there. Okay. What is the sort of orientation relationships which from one crystal to another crystal can have. All this information we can get it using stereographic projection. Those aspects I am not going into it because that is not of relevance are important for this part of these lectures. Okay. These are some precipitates where we have identified on which slip planes they are coming from, the trace and analysis has been done. Okay. This is an involved process, so I will leave it here. But essentially what I have just tried to show you is that how a stereogram can be constructed, okay, or how it is constructed. and it can be mathematically also we can construct it. Okay. That is what is important is that the wolf nut has to be constructed first. That's the one which is the calibration chart with which all this information is being done when we want to manually do it. Otherwise, the softwares, then when you click with the mouse at a particular point, it will always give all the information about it because all the information is inbuilt into that system. It has been fed into it. Okay. I will stop here now. If you have any questions, you can ask. Yes. Yeah. No, actually how it can be done is that there's a way to do it. Suppose you assume that there's going to be a point which is going to be here. You wanted to find out. What you can do it is that put the wolf nut behind it. From here to here, what is the angle? From here to here, what is the angle? From here to here, what is the angle which you measure it? Each of this angle, once it has been measured, okay, you take the sine of it and take the ratio, okay, and that ratio you make it into an integer, that integer corresponding to index of that plane. That you can find out, yeah.
Is there a way we can intuitively kind of say?
Okay, intuitively the way we can do it is that, like from here to here if I take it, this is one stereographic triangle. From here to here if I cut it, this particular point where these two lines cut, this will correspond to 212. See, this is 001, this is 2 vector sum with which you can do it quickly. You understand that? That's the simplest way in which to, but some of them you have to find out appropriately, but that by measuring angles itself of any point with respect to 3 of these coordinates, okay, immediately we can try to calculate it and take the ratio, we will be getting it. That's the way it is done. Okay. It's a very important, not only in, this is used in physics also. There's a lot of abstract physics also, this stereogram comes into a picture. There they represent it always this in complex plane. It's much more complicated the way they look at it. Yeah. Which one? Yeah, orthographic projection you require 2 directions you have to specify, right? You have to look at it to have a projection. In this, only in one projection, 2-dimensional projection, but whenever for civil engineering or machine drawing we wanted to do, we use an orthographic projection. The other projection which we can use it is like a camera. When we take a photograph of that room, this projection is a perspective projection. From one particular point, all the lights emanates and it comes, but the distance information is missing in that. What is being done in a stereographic projection is that the same perspective projection we are doing it from the surface of the sphere, but the 3-dimensional objects, all the points on the object from the center of the object, okay, whatever the line touches is projected onto the sphere and the projection is taken. So that this gives only information about the angles. Only angular relationship you can get it. Okay. This is one method by in which in 2-dimensional projection, all the information about the 3-dimensional information, because maybe if you choose an axis system, one direction is like this, another direction is somewhere like this. This angle, if you have to measure it, in 3 dimension it's going to be difficult. If it can be projected onto a 2 dimension, then we can measure them. That is exactly what it's possible. And then in this, if you look at that, if you look at this one, the area actually on the surface of the sphere, this one, and the area which is going to be on the surface of the sphere, this angle, they are going to be the same. But on the 2-dimensional projection, because area is what we visually see from, but that is what you can make out, that from here to here the angle remains 45 degree, from here to here also angle is 45 degree, but the linear length is going to be different, because in one case it is r tan theta by 2, r tan 45 by 2 you can calculate it, here r into tan 90. So the distance depending upon the tan theta, because the periodic functions, okay, they don't change in a linear way. That's what it is represented here. That's why even on a map, when you look at it, when these latitudes and longitudes are there, once you had marked them with respect to that angle, the area may look that same of different countries in the map when you look at it, But once you look at mark the angle, then only you can find out actually what's the area, which is, if the angle remains the same, it has the same area also. Then there are many other projections are also there, mnemonic projections are there. Then in civil engineering or in many other animations, they have projections from two angles, that is viewing it from here and viewing it from another point. The perspective itself, with they call it the 0 point, from where it starts, all the projection meet, from that you look at it, how it comes. That's called as a ray diagram projection, because many of the animation films which you see it, why they are looking very lively, these are all called ray tracing. That is, from one particular point, if you view it ray tracing, the light is falling from that particular point, then it will be creating a different point shadows of different length and different intensities. That's what really we see it now with our eye. When we see it, only a small difference between these two distances. Otherwise, that light from different regions, the light is coming, there are different types of, I can have a point light source, I can have a light source which is more uniform. Those projections are much more complicated. Then how that information will come, that all they take it into account in the projection, and then that animation is being done, the coloring is given. That's why when we see that, we think that it's like what we naturally see. That is behind this, all these sort of projections are there. No, I have not shown you there are many types of ways it can be projected, because I thought that's not part of this talk, which is not relevant for working on crystal plasticity or crystallography or microscopy, but you can learn. No, if you take a cubic system, okay, property wise, if it is an isotropic, it's not an anisotropic one, then either you take on 001 direction or 001 or 010 or 100, they are symmetric, okay. And the cubic system also, literally angle wise also, if you look at it, they are all going to be asymmetric, okay. Suppose you wanted to generate, one has been generated, okay. If you have to construct the crystal structure by giving an appropriate rotation, this is where the point group and space group symmetry, I can do all the point symmetry operation and generate this entire structure. I could do it in a particular specific orientation. I'll have to just rotate it, another one will come. Like here, if I take it and I take a mirror reflection of it, the next one will come. These are all symmetry axes, okay. That way you can generate it. That's what, if you have to draw it in a computer, you will generate only one particular part of it. Once that is done, you put all the symmetry operations, then the whole system could be generated once we know the symmetry, what are symmetries which are involved in that. That's because of the crystal symmetry. For any structures, when you draw, it will have some symmetry which is associated with it. Like if our picture has to be drawn, if you know the one half of it, that picture, you take a reflection of it, the other half can be automatically put on that side and you can complete the picture, right? Assuming that everything is symmetric, externally we look symmetric. So we don't have the full information, is not necessary. If you know the portion which doesn't contain any symmetry, and then we know the symmetry operation, from that we can generate the full figure. That is how all these drawings are done in computer. Symmetry is very important, because otherwise you have to waste a lot of time repeating that same thing. Eh? Yes, only a sector will be drawn, because all the drawings, if you look at it, they will use only one stereographic, only this particular one will be shown in all of them. Okay, that is good enough. And this particular one, depending upon the symmetry, will change. Here I mentioned that this has got about something like 24 is there. If I see tetragonal, that symmetry will come. Then I will have only 12 will be there, the same. So that changes. That those who are interested can look into these details. So once you know the symmetry, like if I look at a triclinic system, if I wanted to plot a stereogram for a triclinic crystal structure where angle alpha, beta, gamma, they are not 90 degrees, they are not equal to each other, not equal to 90, and ABC values are different, then in this stereogram, the full stereogram has to be drawn complete, because there is no symmetry which is associated with it. Every point has to be calculated and done. When symmetry is there, that makes computational life easier. Okay, if no more questions, I will stop here now. Okay.